Alrighty, so the first half of 9.5 will be about this thing called the cross product. We've already spent a considerable amount of time talking about the scalar product or the dot product. Now let's dive into what this thing called the cross product really is. To get a better idea or understanding of what a cross product is, I want you guys to do a quick demonstration. You can either do it mentally, visualizing your brain, or you can actually do it in front of you. You should have at least paper in front of you if you're taking notes. But on scratch paper, don't waste a perfectly good piece of paper here. It could be on junk mail, whatever you have lying around. But on whatever piece of paper you have, junk mail, etc., just draw two vectors. Now, what I want you guys to do is take this piece of paper and lift it up. Rotate it, turn it upside down, basically move it in the air however you want. Hopefully, and this is a very obvious statement, you should notice that those two vectors that you drew stayed on the piece of paper. Right? So no matter how you turn or twist or rotate or do whatever to this piece of paper, those two vectors that you drew stayed on the surface. Which is why mathematically we say that a plane or a surface can be defined by two vectors on it. So this is a geometrical idea that if we have two known vectors, then you automatically know the surface that it describes. Well, why is that important? Let me go ahead and redraw these two vectors sharing the same initial point. Because a surface is defined by two vectors in physics or sciences in general, we're always interested in knowing about perpendicular vectors. So we want to figure out what vector is perpendicular to the surface. Now, since the surface can be defined by two vectors, that question translates to what third vector is perpendicular to those two vectors. So that third vector, right, that happens to be perpendicular to the given two vectors is what we call the cross product. So this guy right here, this vector, I guess I should do it in a different color. My pen is acting up. It's not drawing a straight line, it's all squiggles. There we go. That third vector is what we call the cross product. So that's it. That's the big idea. The cross product of two vectors is another vector that is orthogonal. Remember, orthogonal is the fancy word of perpendicular. That is orthogonal to both vectors. And of course, by extension, since two vectors define a plane, a cross product is a vector that is orthogonal to a given plane as well. So, conceptually, that's pretty simple. A cross product is nothing more than a perpendicular vectors. In high level math, in calculus, or in your science classes, in physics and engineering, whenever you need a perpendicular anything, a perpendicular vector, a perpendicular EM field, etc., 9 out of 10 times that's going to involve this cross product thing. Now, since this is not a physics class, since this is not an engineering class, we're only going to be interested in how to actually compute it. So I want you guys leaving this class being able to do the cross product so that when you guys do go into engineering or physics, you guys can spend more time on the conceptual stuff rather than the computational stuff. So we'll handle the computational stuff here. So there are two ways to go about the cross product. One way is just rote memorization, which I'm not a big fan of, and the other way is, to me, nicer to remember because it builds upon something you should have done in the past, which is matrices. So let's talk about the cross product. Here's the formal formula. The cross product reserved only for three-dimensional vectors. So it makes no sense to talk about the cross product of 2D vectors. This is only for three-dimensional vectors. So if I have two three-dimensional vectors, say vector u, in component form, so let's call it x sub 1, y sub 1, z sub 1, and vector v, call it x sub 2, y sub 2, z sub 2, then the cross product, which we will denote with the typical multiplication cross. So that's why when it comes to vectors, you have to be careful with your notation. An x for multiplication is reserved for the cross product. A dot for multiplication reserved for this, obviously the dot product, the scalar product. So be careful of your notation. Now the cross product is a vector, so the answer won't be a single number, but an actual vector. And I'm going to be honest with you, this is something I've never memorized, so I actually have it written down next to me so I can write it down for you. But this is something I've never actually memorized in this way. So the horizontal component is y sub 1, z sub 2, minus z sub 1, y sub 2. In other words, the y of the first times the z of the second minus the z of the first times the y of the second, comma. The y component is going to be z sub 1, x sub 2, minus x sub 1, z sub 2. And then the last component, the z component, is going to be x sub 1, y sub 2, minus y sub 1, x sub 2. So you are more than welcome to just blindly memorize this. Again, some people do, right? Some people are good at memorizing stuff. I am not, so I've never actually memorized this. But that is the legitimate formula to find the cross product. It's just a simple plugging in numbers and computing them. And if you're happy with just blindly plugging in numbers, blindly following formulas, good to go. You can come up with your own tricks, your own observations. There is a set pattern to this, so I'm not saying don't memorize it. I'm just saying I particularly never have, because I much prefer this alternative definition. So an alternative definition of the cross product. And I don't know, maybe it's because I grew up during a time where matrices were studied heavily, so I was knowledgeable with matrices. I know if you were in my Algebra 2 class, we definitely did spend a considerable time on matrices, so you should have done determinants before, so on and so forth. So this is something I'm far more comfortable with because it's easier for me to remember. So it has the same setup. If we have two vectors in component form, the u sub 1 is vector u is x sub 1, y sub 1, z sub 1, and vector v is x sub 2, y sub 2, z sub 2. Then the cross product of those two vectors is defined to be the determinant of a 3 by 3 matrix. Now the setup of the 3 by 3 matrix is always the same. The first row will always be the will always be the unit vectors in all three directions. The unit vector I, the unit vector j, the unit vector k. So that's easy to remember. It's always going to be like that. Now the other two rows are just your two vectors. So it's easy peasy. And really, the order doesn't really matter. We'll obviously go in order. The sub 1s will go first and the sub 2s will go second, but it really doesn't matter. X sub 1, y sub 1, z sub 1, x sub 2, y sub 2, z sub 2. That's it. So that is the alternative definition of the cross product, and either way will give you the correct vector. The important thing is you always want to expand on row 1, right? When you calculate the determinant using the cofactor expansion, Testing, testing. Sorry about that. I had a little technical difficulties with my microphone. Um, Guess I'll just stay in the final cut because I'm not a video editor. As I was saying, when you find the determinant using the cofactor expansion, you typically want to expand on the first row. So throughout the note, if you forgot how to do determinants with matrices, I'll show it when we do the few examples in today's note. So I will be using the alternative definition, just to kill two birds with one stone, to teach you how to compute the cross product as well as to refresh your memories on determinants of 3x3 matrices. Now, if you don't want to do all that, if you just want to say, hey, Mr. Vo, I want to be a robot, I want to just blindly follow a formula, well, there you go. Have fun. Right. So notice this is a part A. I'm not going to ask you to do too complicated things today. Our main goal is to be able to compute the cross product today, be comfortable with it, so tomorrow we can do stuff with the cross product. So again, today we just want to find it. So let's just do a quick example here. Remember, the cross product is simply, um, finding a perpendicular vector to two other vectors. So, for example, suppose vector u is, I don't know, 0, -1, 3, and vector v is 2, 0, -1. Fine, and this is a two-parter. Part A. Find a vector orthogonal to both vector u and v. And part B, find a unit vector orthogonal to both u and v. As is typical with these multi-part questions, part B will follow directly from part A. And once you solve for part A, it basically leads your way for part B. So let's do this. So this should just be a straight up application of the definition. So again, if you want to use the plug and chug formula, be my guest for today's notes. I'm going to use the matrix definition. So if I want to find U cross V, I need to find the determinant of I, J, K, and then I lay down the two vectors, 0, -1, 3, 2, 0, -1. So let's refresh our memories on cofactor expansion. So cofactor expansion requires you to expand on either a column or a row, but for the cross product, you typically always want to expand upon the first row. It makes things a heck of a lot easier. So what you do is you write down the element. So this is element I. And then what you're going to do is you're going to eliminate the row and column it is in. Notice it creates a smaller 2x2 matrix right here. You find the determinant of the resulting matrix, which we call a minor. So -1, 3, 0, -1. So that right there is the first bit for the first term. And then you just rinse and repeat for every single term in the first row, alternating positives and negatives. So when I'm going to color code this. So when I take a look at the second element, notice how I was positive. Notice I put a positive there. For the J, it's going to be a minus. And then I eliminate that row and column. And what matrix is left? 0, 3, 2, -1. Then I move to the third element and alternate back to a positive. Okay. And then when I eliminate the column and row, what matrix is left over? 0, -1, 2, 0. Now, then all you have to do is compute the 2x2 matrices. And again, to refresh your memory on finding the determinant of a 2x2 matrix, it's sort of this crisscross subtract business. So you multiply these two guys here. So that -1 times -1 is +1. And then you minus the other product here. 3 times 0 is 0. And that's attached to your I. Minus, crisscross subtract, so 0 times -1 is 0. Minus 2 times 3 is 6. And that's your J. Plus, crisscross subtract, 0 times 0 is 0. Minus 2 times -1 is -2. And that is your K. So when you simplify everything, you end up with I. This right here becomes a +6, so that's plus 6J. And then this guy right here is a +2, plus 2K. So you can leave... the vector should be on the K, not the 2. So, I mean, I suppose, technically, you can leave your answer. If you're doing it this way, you could leave your answer in the IJK notation. But remember, this is the same thing as 1, 6, 2, or if you feel so inclined, get fancy, use the stacked vector notation. All of those are equivalent. So that's easy peasy, right? So you can see how I was able to compute this rather easily, and I didn't have to look at my notes, I didn't have to scroll up to the formula, because me personally, because I grew up doing a lot of matrices, I know how to compute a determinant of a 3 by 3, and it's very easy for me to remember. Just put the I and JK in your first row, and put your two vectors in the second row. That is a lot easier, for me personally, than memorizing all of this gibberish here. But they are 100% equivalent. So for part B, it says find a unit vector that's orthogonal. Basically, what I need to do is convert our answer from part A, because remember, the answer part A is already orthogonal, so we have that part down. We just need to convert it into a unit vector. Recall that to convert any vector into a unit vector, you simply divide out its magnitude. I'll go ahead and rewrite it for our notes here. Recall that for any vector u, if you divide out its magnitude, that quantity is a unit vector, right? So we already have the orthogonal bit, we just need to do the unit vector bit. So we need to figure out the magnitude, right? So the magnitude of u cross v, so this is just, the magnitude formula in 3 dimensions, is the horizontal component squared plus the y component squared plus the z component squared. So what is that? 36 plus 4 is 40, 41. So we just simply need to divide it out. So therefore, the unit vector that's orthogonal to vector u and vector v is, we'll use the angle bracket notation. So it's 1, 6, 2 divided by square root of 41, which equals, you just go ahead and divide each component by that radical. 1 over rad 41, 6 over rad 41, 2 over rad 41. I think the textbook probably just left this factored in front. They probably wrote it like this. Let's do this. They probably factored out that 1 over rad 41. Just know that they're all equivalent. So this is what I would probably do, but don't be surprised if this is what you see on the answer key. They're all the same. So, all right. So finding the cross product is very simple. It's just a calculation. That's all I'm asking you to do. Can you compute to find this vector, right? And again, the important thing to take away here is the cross product. What does it give us? The cross product gives us a third vector that is perpendicular to the two vectors that are crossed, that are used. Sometimes they may ask you to find a vector that's perpendicular to a plane. It's going to sound like the instructions are very different, but as our beginning exercise showed, a plane is just the same thing as two vectors, right? because if you have a plane, you can find two vectors that define it. So for example, suppose I asked you to find a vector perpendicular to the plane that passes through the points, say point P, which is 1, 4, 6, point Q, that is -2, 5, -1, and Q, and let's say OPQR, so I have to sing that song to know my alphabet, 1, -1, and 1. So I want to find a vector perpendicular to the plane that passes through the points P, Q, and R. Now, I know this sounds like a completely different problem. Whoa, this got more complicated. But conceptually, this particular example, this particular problem should be 100% the same as this problem here. Because again, as our beginning demonstration demonstrated, a plane is defined by two vectors. So if they give you 3 points, all you need to do is create two vectors from it. And now remember, when you do this dot product here, let me go up to my original picture. That cross product will be perpendicular at the shared initial point. So I need to create two vectors from these 3 points here that share the same initial point. So you can create any point, P, Q, or R. You can make any of those 3 points the quote initial point. It really doesn't matter. Since it comes first, let's make P the initial point. So I'm going to define vector U as going from P to Q. So this should be a quick exercise. We did this in, what was it? Was it 9.3, 9.4? I think we did this in 9.4. Can you come up with a vector given an initial and terminal point? So what vector describes going from point P to point Q? Hopefully it shouldn't take too long. That would be -3, 1, and -7, right? To go from 1 to a -2, you have to subtract 3 for the x's. To go from 4 to a 5, you have to add 1 to the y's. To go from a 6 to a -1, you have to subtract 7 from the z's. And then we'll define vector v as P to R, right? So notice they have the same initial point, point P. If I go from x equals 1 to x equals 1, I didn't move anywhere, so that's 0 for the x's. To go from y equals 4 to y equals -1, I had to subtract 5 from the y's. And then to go from z equals 6 to z equals 1, I had to subtract 5. So there we go. So to answer the question, you just cross them. So we're going to do u cross v. So I'll do the determinant method again. If you want to just follow the formula, go ahead and just follow the formula. So you have the I, j, k, and lay down your two vectors. So start with the I. So if you cross these out, you get a 1, -7, -5, -5, minus the j. So if I take the j, cross them out, I'm left with -3, -7, 0, -5, plus the k. So if I cross that guy out, -3, 1, 0, -5. So crisscross subtract, so we get -5 minus a 35. So what's that? Is that a -5 minus 35 is -40. Minus, so this is a 15 minus 0, so that's easy, that's 15. That's my j. Plus, so that's a positive 15 minus 0, right? This is 0. So that's a 15 again. Okay. I don't like INJ notation, so I'll convert it to the angle bracket notation. So what vector is perpendicular to this plane? The vector -40, -15, and 15. Right. One little sidebar conversation. Notice how the instruction says find a vector. It's not unique. Find the vector perpendicular, because technically speaking, there are an infinite amount of answers. Because it didn't say unit vector, since it didn't put any restrictions, any vector in the same direction as this guy is a valid answer. So you could multiply this vector by a non-zero constant and technically produce the same answer. So, if you divided everything by 5, technically the vector -8, -3, 3 is also perpendicular to the plane. If I multiply it by -1 and get, vector +40, +15, -15, that technically is the right answer as well. So just be mindful that if you're doing this on your own, and heck, we chose point P to be the initial point, but what if we chose point Q to be the initial point? What if we chose point R to be the initial point? You should get the same answer numerically, 40, 15, and 15, but it may be in the opposite direction. So if you're doing this on your own and you're checking the answer in the back of the book and you realize, hey, my answer is exactly the same, but it's in the opposite direction, it is technically fine. It is technically the correct answer. So just be mindful of that. That the representation of the vector perpendicular may not be unique. So that's all I want you guys to do for part A. There's still a lot we can do with the cross product, but I want to take things slow and steady. I want us to crawl first. So by the end of today, you only have one lesson objective goal. If I give you a cross product problem in front of you, can you calculate it? Because we need to be a master at it before we apply it. So that is it. Good luck. And if you have any troubles, as always, let me know and I'll try to help you. That is 9.5a.